Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everyone. Thanks very much for coming to the talk. It's our great pleasure to have Alexander Kuzmanovic to come here and give us talk on ISP-enabled behavior ad targeting without user consent. Alex got his PhD from Rice University in year 2005, and then he joined Northwestern University, and now he's assistant professor in Northwestern University. His interest is in computer networking with emphasis in measurement, analysis, and protocol designs for all kinds of internet algorithms and protocols. Without further ado, let's hear what Alice has to say about this interesting topic on ad targeting.
Thanks, Gene, so much. I'm really happy to be here at Microsoft. I always liked Microsoft better than any other operating system. I'm a Microsoft kind of guy. I hate Macs. This can go online. This is my official statement. And so basically today I'm going to give you a brief outline of 4 projects that I'm my group is working on. So this is going to be a breadth kind of talk. I'm not going to go too deep into some technical details. I'll just put 4 different ideas to you. So if you're interested in learning more about it, you can read a paper, you can ask for a paper, you can talk to me. I'll be happy to answer all these questions that you might have. So this is also good for me because you will not have any chance to ask any questions because I'm going to be talking very fast. I'm going to be moving from one topic to another. By the time you have a question, I'm going to be talking about another topic. So you're not going to have any opportunity to ask any questions. That was a joke, of course. So let's go straight to the first problem. The first problem is can we use search engines to do networking research? And the scenario I have in mind is a student goes to a search engine, puts a title of his projected PhD thesis, and the thesis comes like 10 different versions of the thesis. Student then goes, reads all these different theses and says, okay, this is the one I like, this is my PhD thesis, and he gets his PhD. Now, this is, of course, not possible. That was another joke. So basically, what I'm trying to, that is still not possible, but other things are possible. So if you put a random IP number in a search engine such as Google, you can end up having a different information coming out of that search engine. So for example, this particular IP address is associated with the Gnutella network, right? So basically, and you might get surprised that if you start putting different IP numbers in different search engines, huge amount of endpoint information is available on the web. So the problem we try to answer is, can we systematically exploit search engines to harvest endpoint information available on the internet? So basically, before I try to answer this question, let me first explain how, in the first place, do all this information come to search engines in the first place. So basically, there are a number of reasons why information about endpoints can end up on the web. One example is, for example, popular servers, for example, gaming servers. IP addresses are listed and available on the web. When they're available on the web, they get they get indexed by search engines, and they end up being there. Then, when you go to a website, you might think that that's your own thing, that you visit a given website. Well, information about websites that you visit can, all these websites can run logging software and basically display statistics, among others. They can show what kind of IP addresses are they accessed from, right? Then if this is not enough, you might go through a proxy network. Well, you have a number of proxy systems that actually go on and display logs, and they become publicly available on the web. And then, even with peer-to-peer systems, Information is available on internet for a number of different reasons. For example, whenever you're accessing a peer-to-peer system, you have to go first through a public domain, and basically to get the information about the files that you want to access, this becomes again publicly available. And of course, there exists a number of blacklists, panelists, spam lists, and so on and so forth that you can actually. This is another source of information that gets publicly available. So what we did is we designed a methodology. So I'm not going to spend a lot of time here. I'm just going to give you a brief outline of our methodology on how do we go from a given IP address to tagging that IP address with appropriate properties of this IP address. For example, what kind of activities are associated with this particular IP address. So basically here we, again, Google is the search engine that we have used. When you enter an IP address, you end up with the number of URLs and the hit text, and then we try to look at the domain name itself to try to understand what this IP address is about. So there are examples when you can directly from the domain name realize what the IP address is associated with. For example, if you have DNS server in the domain name, this implies that this is information about that. Of course, not always is this possible, and hence we do something else. Again, from the artificial intelligence point of view, this is really a toy problem. This is not our main contribution. So if you are an AI person looking for some deep things here, this is not the place to look at deep things. This is just a small hack by a couple of networking people trying to go to something else that we know better. So basically, and then once you end up with this, you go on and tag this IP address with appropriate features. So a single IP address can be tagged by a number of different features. Okay, what is this good for? Well, this is good for example, understanding what applications people are using across the world without having access to their network traces. It is hard to obtain network traces. You go to ISPs and says, can we have some network traces? They will tell you, no, you can't get that. There are security issues, there are privacy issues, and you can't get that. So with this approach, you can go on and analyze different networks, try to understand what kind of information is available on this network. So I'm again skipping a huge part of this problem. In the sense that, so basically what we managed to obtain through our collaborators bucket level traces from a number of different places in the world. And then what we did, then we compared information gathered from these bucket level traces with our approach, where we just go on and simply input one by one IP addresses and try to understand what is going on. And then the key insight here is that you can, if an application is very popular in a particular region, we are capable of capturing that in both the traces, in both the packet traces and by using our approach. Of course, our approach is incapable of telling you, okay, this is the exact way that different applications are used and so on, but it can still give you, if something is strongly shows up at a given region, we're capable of capturing that.
Now you're talking about web-based applications? Because how would you know if they're using Word or Office or Excel or running some PC-based game on their computer just because they're
I'm talking, so the question is, how do we know what kind of applications am I talking about? How do I know if they're using this or that type of application? So what I'm talking here is, when I'm talking about applications, I'm talking about application 1 is streaming video, application 2 is web, application 3 is peer-to-peer, and so on and so forth. So I'm not talking about client-level applications.
So you described you did some validation of the quality of your inferences that are coming out. It seems for somebody to actually use this in practice, like, do they have to keep validating the system? Because, I mean, it seems that it works in the present. It seems might not have any bearing on whether or not the technique would continue to work in the future.
Because?
Because of all these harvesting methods that are there are very application specific. Whether or not a client gets logged by using some network application, it's very, it's almost accidental that information gets stored, and it gets stored because of a lot of reasons, and that may or may not exist for certain applications.
I can agree with that to some extent. So I have to repeat my claim. My claim was that if something is heavily present at a given region, we were capable of getting that. Now, is that I agree that there is a lot of how do you know if a given application is being actually reflected on the web? That is a huge problem, of course. But the claim here is that if something has strong presence at a given region, it does leave a sufficient trace that we can. That's what we have seen. Today.
Yeah. Okay.
Yeah.
Sure.
I mean, it's one of those unknown things, right?
No, yeah. Just coping. I'm not saying it's yet. Yeah. But it's
Sure.
Yeah.
So again, this is I agree. This is the most shaky application that we came up with this approach. This is just one of the applications that we're using. So I'm next going to explain the second one, which I hope will convince you it's not as shaky. But I do agree that there is a lot of uncertainty here. The way we treated this uncertainty is that we simply compared with the ground truth from 4 different places where we were capable of gathering packet level traces, and it worked out. Is it going to work in the future? I don't know. We'll see. So the next application is the traffic classification problem, right? Assume you do have access to packet level traces. How can you figure out what is going on? What kind of applications are used there? So current approaches are port-based, payload-based, signatures, numerical and statistical analysis, and so on and so forth. You're trying to understand what is going on. Now, what we are doing here is that we are saying that, okay, use information about destination IP address available on the internet, right? And this you can get using our approach. Once you use this approach, you can get a much better granularity of your inferences, and you can classify a much larger percent of traffic. And then here I'm comparing to another technique used by to another traffic classification approach. I'm not going to talk about them because that's not the point here. The point is that we are capable of performing much better traffic classification than they are. So on x-axis, you have the sampling traffic. This is how many packets do you take randomly out of from a packet stream. And on the y-axis, you have the percent of traffic classified, right? So what it is showing that we are capable, and these lines are for 2 different networks that we were capable of gathering packet level traces. So what it shows is that when there is no sampling, you get all the packets. We are much better than they are. However, when you have sampled level traffic, their approach totally goes down, while we are capable of having high classification capability. So the bottom line is that despite huge sampling rates, we are still capable of classifying large amounts of traffic simply because we are based on a single packet, we are capable of saying, aha, given the destination address, we looked on a search engine, we know what this is about, hence we can tell you what it is. So I will leave it here for this, for the first topic. If you're interested, you can. I'll be happy to talk more about this project, and you have some information online as well. So let me jump to the second problem that I'm going to be talking about today. This is the ISP-enabled behavioral ad targeting. So basically, the question with the first project was people started telling us, "Oh, you guys are promoting Google. Why did you put that in the title? That's not fair, blah, blah, blah." So we're not promoting Google. We just use that as a way to promote our paper, right? So, and basically, let me explain. The second project actually goes in a way against Google's approach of doing some things. So I'm going to explain that next. So the second problem that I'm going to talk about is behavioral ad targeting. So basically, behavioral ad targeting itself is a huge business. It's a $20 billion industry. And then basically all the banner ads, rich media ads, email marketing, all that stuff that comes to you when you're looking at a given website, that is comes under online ad targeting. And then behavioral advertising is a part of this ad targeting business. And then to simply explain how it works, for example, you go to user A accesses site X. Site X belongs to category P, for example, sports. So the next time user A accesses site Y, well, the advertisement of type P is going to show up on that website because you have shown already interest in that particular activity. So to look at the market share in this behavioral in the ad targeting business, Google owns 35% of the business. DoubleClick owned 34% of the business. Google bought DoubleClick, hence 35 plus 34 equals 69. 69 greater than 50. So where I come from, this is called monopoly, right? In a given business. So internet service providers, on the other hand, yes.
Quick question: that 35% that's revenue based or is based on?
It is based on the number of clicks to ads or something like that. I can give you more precise.
Meaning
Impressions.
the number of ads.
The number, yeah. Okay, so internet service providers for years looked at these things and basically see that these web-based companies are taking a lot of money while they are putting all this infrastructure, shipping packet from point A to point B here, they're not gaining as much money as they would like to. So the question they asked is like, hey, how about we do behavioral ad targeting, right? So here you have all the packets from a user are going this way, right? So if they do the packet inspection, look at the packet and try to understand what information are users interested in, they can gain the same information. Right? Then they can resell this to ad targeting companies and they can gain some money as well, which sounds like a reasonable approach. However, the problem here is the legal one, right? So internet service providers are, as broadband providers, they, this law, which is Federal Wiretap Act, applies to them. And it does not apply to the web-based companies. And it says that those shall not intercept the contents of communication, which can result in civil and criminal penalties. Right? So it is illegal for ISPs to look at the packet payload to understand what is going on. And there was a huge pressure on basically ISPs to not to do this, both from consumers and from the federal government and so on and so forth. Yes?
It's okay to look at addresses and destination addresses, or?
That's what I'm going to talk about next. It is okay.
This is black and white legal stance.
So here it is. This law came out in 1969, and it was designed to prevent phone wiretapping, and it was enacted again in 1986, before the internet was around. And they say this holds for computer communications as well. And now, in 2009, ISPs are unable to do this stuff because of a law that came out in 1986, which kind of doesn't make sense, right? And there is no fairness in this market because web-based companies are capable of doing this without any problems.
I disagree with your stance on that. Basically, there's a conversation between the user and that website they're going to. And so that is the conversation that is actually sanctioned. To look into that conversation by looking at the packets going back and forth, to me, is a third party who is not part of that conversation.
That's what the whole argument is all about.
And the second part is that website has a privacy policy so that the user understands it. The user can't get access to what the ISP is supposedly doing because the ISP is not visible.
So my point here is that it's not the same it's not the same game for ISPs and web-based advertisers currently. And I think it should be the same game. Right?
No.
Why not?
I didn't call the ISP. I called Amazon, or I called eBay, or I called somebody else.
Sure.
If I go to my ISP's website, yes, then I agree. But if I don't, then why is the ISP jumping in the middle? I wouldn't want my ISP to get what I'm doing.
Are you aware that your communication is being monitored by Google and by DoubleClick? Are you aware of that, or no?
Yes. When I go to that website,
did you sign up for that or no?
When I go to that website,
did you sign up or no?
But you don't sign up for any of those things. You don't sign
That's
up
my
for
point. My point is that there should be some fair game here, right? And it's currently not there.
No.
Okay, so let me.
Privacy policy exists on the website you go to.
I mean, your web browser is full of Google and DoubleClick cookies, and users don't know about that. And that's it should be the same principle. So what I'm saying here is that this is currently used against ISPs to basically do behavioral ad targeting. What we're saying is that doesn't have to be like that, right? So you can turn around the law. If that 1986 law was wrong, well, we can use another law to do stuff. So basically, what we were looking at is, and I will tell you that I have consulted with Paul Ohm from University of Colorado, who is an expert in these issues. And then basically, another piece of law is Electronic Communications Privacy Act, which states that any provider can hand over non-content records to anyone except the government. Now, what this means is that TCP headers could be legally shared. They are non-content-based communication patterns of communication between endpoints. And then the research question we wanted to ask, well, once you have TCP headers that you can legally share with anyone except the government, can you, based on them, do behavioral ad targeting? And we claim it's possible, right? So, and again, I will come back to this legal issue at the end of this part of presentation, because I do agree with you that users should be given the right to say, I want this to be monitored, I don't want this to be monitored, but it should be equal for everybody. It cannot be that ISPs are some kind of bad guys and these other web-based companies are good guys, so they can do it without any questions. So the research question is, can we do this? And then our approach is that you can do this. Basically, you can go on and collect statistics about web pages from a given website, and then you can compare that to extract web-level information available from TCP packets. So once you compare these two information, it becomes possible, I will show, to basically understand content-level information based only on non-content-based communication. Okay. Web profiling and collecting statistics about web pages. So basically, I'm not going to go too deep into this, but the bottom line is that basically web nowadays is a fairly kind of complex beast. So what we have here is basically each web page consists of a root file. This is the index file, and then you have a number of different objects that comes with that. So basically, so the first distinction is the root file versus object files. Now, object files could be transferred in different various transfer modes. They could be compressed or non-compressed. Then you have a use of content distribution networks. So these objects could be stored internally on the website or externally on a content distribution network. They could be cacheable or non-cacheable. So the bottom line here is that there is a huge, significant statistical diversity among pages at a given website, right? And then this diversity could be used to basically understand differences among pages, even if you don't have direct access to them. So this is one piece of the puzzle. And then the second piece of the puzzle is that you have, once you look at the TCP level traces, what can happen is that you can basically go on and understand there is a lot of reflection from the web kind of web layer down to the TCP layer, right? So the bottom line here is that if you observe packets generated by a single user, you can say, aha, these packets belong to one page because there is a natural delay between streams of packets sent by or requested by a single user among different pages. Now, this is one thing that we're using. And at the same time, but looking at the TCP headers, I'm not going to go into details here, but you can actually distinguish which of the web pages are, which of these elements are, you can distinguish different elements at the TCP layer, right? You can say this is one object, this is another object, this is a root page, and so on. I'm not going to go into details here. I can send you a paper. It's a fairly straightforward thing. There's no huge science here. OK, so once you have that, this is how our system, these are the results. So basically, we had 6 different websites that we were exploring. New York Times, Football Club Barcelona. We did this before they became European champions. IKEA, Toyota, and then 2 of the universities. One is Northwestern, the other is University of Granada. So what you can see here is that the success rate, which is the probability to successfully detect which page was accessed, is around 85% in all cases, and the false positives are below 5% in this particular case, in all the cases. So, yes.
What's success here? I'm sorry, I missed that.
So the basically, you have a user who accesses, let's say, 100 web pages. Out of this 100, we can say 85. We can detect successfully 85 of these 100 web pages. And for the 5 pages, we do make false positives. We say these pages were accessed while they were actually not accessed.
Without looking at the HTTP header.
Without looking at the HTTP header. Only looking at the TCP header. OK, so the next thing that we looked here is that, OK, this is OK. But to do something like that, an ISP would have to crawl a lot of websites, right? Because you have to build a profile about a large number of websites. This is one thing. And the second thing is if you are an ISP and you collect all these TCP headers, you want to ship this to a third party, to an advertising company, it takes time, right? It can, you put this on a device, then you ship it there, some time can pass. So the question is, if you have basically non-perfect crawling, so for example, you can crawl a website only once per week or something like that, or once you ship data from an ISP to an advertising company, the question is, can that hurt the performance that we see in this basic case? So the answer is yes.
You still rely on I'm guessing why is the advertising company getting this information from the ISP and not the site that the user is going to?
That's not what you're thinking about. ISPs want to basically get into the business of advertising. They want to
intercept the bytes. Assuming that they are not intercepting traffic, they are not actually changing content being served to the clients. So the advertising company, it seems like, is better off.
Then you have to collaborate with tens of thousands of websites that users are accessing, while here you collaborate with a single ISP who has all the information about the user. Because whatever goes through that ISP sees that. And then whatever site that user accesses, if that site is not collaborating with the advertising company, you don't know that happened.
Well, the site must be collaborating with the advertising company because the site itself is placing.
Not necessarily. I mean, there are different advertising companies.
It's better to create user profiles
at the source
side than on the server side.
Yeah.
It's simpler.
Well, either way, I mean, it's an extra source of information, right? If it could be produced, it would be valuable. I guess my question is how much granularity is necessary? I mean, just knowing the IP address of the server, New York Times versus IKEA, right? Is that enough to go on?
So that's a very good question. In some cases, you might, for sure you would like to have more granularity, right? If I'm going to IKEA, I want to buy some furniture. What do I want to buy, right? Am I looking for I mean, that can basically fine-tune that advertisement that comes to me at the end, and it increases probability that I'm going to actually click on that advertisement later. Or if I look at New York Times, it's a fairly diverse thing that I can be looking at. If I'm looking at car prices, that implies that, I might be interested in looking at cars, so hence a car advertisement may come to me. So more information is always good, I think. Even though in some cases it can be fairly straightforward, like if I'm looking at Football Club Barcelona's website, I'm interested in football and in sports, right? Maybe that granularity is not necessary at that particular case, but there are other cases where it is important. And we should write papers, right? So we have to do something here. Yes?
Good question. So the server IP address is used to classify which site the client goes to?
Yes.
So this is like Akamai complicated?
No. So we look at that. So we only look at the basically we classify destinations as going to the server side or to a CDN. So any Akamai or any other stuff is just external information. We use that to understand what kind of web page did the user access, but that's the only thing. We are not looking at the IP addresses of particular Akamai servers and stuff like that. That's not what we're doing. We just say internal versus external. Internal means you go from the origin server. External means you look at CDNs, irrespective of what CDNs.
Then all the different accounts mixed together as you go to that particular external, I don't know.
So typically you would get some content from the origin server and the rest from the CDNs. Yeah. Okay. So basically the question here becomes if the traces are all. So that means you ship traces to a given advertising company, yet sometimes passes, like a week goes on. Right? The question is, can you still use these traces? Can they still be useful? So we compare all traces with current web profiles. And the bottom line is that you can still get, basically nothing changes over time in the sense that you can still get high success rates and low false positives. And why this happens? Well, because for these three particular sites that we are looking here, Toyota, University 1, University 2, the change rate of a site is fairly small. So that means that both the root pages and the objects on that, their size does not change dramatically over time. Hence, we are still capable of reusing these traces.
So where in the New York Times?
I'm going to show that next. So next, the question is what happens with these more changing websites. And then here, what we are looking here is that we capture TCP trace at the last day, and we have the profile of New York Times from 7 days ago. So the question is, can we still do a good job? So this shows you that we can still do a good job. New York Times here is blue, and it doesn't change dramatically over time. Why does that happen? Well, if you look at the change rate, for New York Times, it's quite high. 60% of pages change over time, right? But these are mainly root pages, index pages. So if you have a given page, people can leave comments and all the other stuff, and hence that thing does change. However, the objects on that website, which is this particular graph picture, is here. They don't change dramatically. It's a very small change, like below, like 5 or so %. So the template of a page stays the same, while the content can change, but the template stays the same. So you still can do a fairly good job in distinguishing different pages, despite the fact that the content in this environment does change, often because people leave comments and do other stuff there. Okay, so to summarize, the key motivation for this work is that I believe, and my students believe, that online advertising business needs more fairness. Right? We also strongly believe that users should know whether their traffic is monitored or not. So basically here we have shown that the law itself is quite outdated. Because you can take one piece of law and say, aha, you can't do this, but we can take another piece of law and say, well, you can't do that. You don't even have to take consent from users, right? You don't need even that, right? So the bottom line here, what we are arguing for, is that we need a comprehensive legislative reform that would put all these things in some kind of to make a fair game out of this whole stuff. And we, of course, believe that this should not be, such a reform should not be used to kill academic research. That means we researchers should be given a lot of data that we can look at. And because once we have access to a lot of data, we can do a very nice things. So this is basically introduction to the third project that I'm going to talk about. Measuring serendipity in a mobile 3G network. We were given a very huge trace from a mobile operator. Yes. Yes, you want to talk more.
Deep packet investigation, DPI, has been trounced by lots of industry experts, privacy advocates, governments, because it seems to be inappropriate and very little value to consumers. So as an ISP, you ask me if I want you looking at my packets and when I want to opt in or opt out, it's like, what do I get from it? Well, you get to sell my data to someone else and make money. Do I get anything? No, you get to look around at what I'm doing. So why is that unfair and why is that necessary to help research? Why would I want to do that?
Yeah, but how is, I mean, Google does the same thing, exactly the same thing.
Tell me how they do that.
Because that's how the whole online advertising business works. I'm sorry, what?
Google is not an ISP.
That's exactly true. But Google is doing exactly the same things that I'm saying the ISP should be given opportunity to work with. Why not?
The scenario is not the same.
I get to choose Google. I mean, it's a free service. I don't have to use Google. I don't have to enable cookies, right? But I mean.
But you have them enabled right now, and you don't know about that.
That's a different issue.
It's not.
It's not a different thing. No. What I'm saying is, and this is really the. I mean, never mind. But I can send you. I mean, there are other opinions that it should be fair. It should be the same.
I agree it should be fair, but this is not fair because they're not the same. They're not apples and apples. I go to a website, I can actually choose to say I want to opt out of advertising for DoubleClick, for Google, for Microsoft advertising.
If it is opt out, it should be opt out both for these guys and for the web-based advertisers. Because now Google and others are saying, oh, you guys, you are very bad guys and the law is not on your side, so you should apply an opt-in approach. Right? So why doesn't Google apply opt-in approach?
I get free content from a website. In return, they show me ads. The ISP is not giving me any content.
We fundamentally disagree on this. I would like to move on. I'll be happy to discuss more.
You're right.
Totally. Okay. Yes.
I don't want to discuss more about this, but I just want to point out that, I don't know, as computer scientists, I'm a little uncomfortable sort of trying to interpret what the law says, especially when there are no sort of cases that establish what exactly, how the courts interpret the law. And I just find sort of like motivating problems based on my or yours or your interpretation of the law as computer scientists is sort of shaky, right? Because I'm not a lawyer, I don't understand what's going on. I can read that, I have an opinion, sure, but it's just my opinion.
So basically, I mean, I agree with that to some extent. I'm just saying that that there's a lot of opportunity to come up with interesting research problems if you look from that perspective.
The motivation is, look, by doing deep packet inspection, you open a huge can of worms, and you can do a nice job looking at the TCP/IP header.
Yes. I know.
That's great. I'm sort of like debating what the law says.
We had a SICOM reviewer who had exactly that point. Yeah, that's a very good point.
It wasn't me.
Yeah. Okay. No, I didn't imply that. Okay, let me move on very quickly. Because I have other things to talk about, and I'll be really happy to discuss further this issue because I see it's kind of important. So so the motivation here is that once researchers are given a lot of data, it's great. They can do very interesting things. So in this particular case, we had a lot of fine-grained data from a mobile operator. And at this point, we were not looking at law or anything like that. We just, once you get the data, you forget about the law. You just do your research. OK, so the bottom line here is that to motivate this quickly, social networks are becoming very popular these days. But some believe that the future of social networking will take place on mobile devices as opposed to being just limited to desktops. So some of the applications that are being enabled with this technology are so-called serendipitous discovery of people, businesses, and locations. So basically, what does it mean? For example, if you go to a neighborhood, and then your friend is in the same neighborhood, if you're in the same vicinity geographically, you can go on and basically hook up together. This is an application offered by Looped, a company from New York. Another example are like behavioral ad targeting, like businesses. If you go to a given area, and if this business knows of what your interests are, they would be happy to send you advertisement on this. Now, users are not happy to receive those advertisements often, but that's a different question. And then locations, for example, you can do tagging. For example, you can go on and you can go to a restaurant. You like the restaurant. You put this on and send this to your friends. Your friends are in the neighborhood. They see, aha, that was a great restaurant suggested by a friend of mine. I'm going to go there. So what I'm arguing next is that core-grained location information is very useful for these services. Now, why am I saying this? Because we got hammered by some reviewers that we have a fairly coarse-grained information in our data set, which consists of basically base stations. And that's not sufficient to basically converge to these kind of services. I argue against that. So the point is that even if you have coarse-grained information at the level of a block or of a base station or a city, that is still useful because that can help you hook up with friends. And at the same time, users are more comfortable sharing coarse-grained information than GPS-level information. This is another argument that people say, really showing telling exactly where I am on the map is maybe not that secure or private or whatever. So the question that we try to answer here is that what is the relationship between mobility properties and application affiliation in the cyber domain? So if you are interested in a given location, how does it affect your mobility properties, and how does it increase or decrease the probability to meet others who share the same interests? So let me just give you a brief description about what we were doing. So here are the details about our data set. So we had more than 3 million packet data sessions on more than 280,000 clients. And we had close to 1,200 locations in the greater Chicago area. And then we were trying to understand what is happening with all this stuff. So the way we extracted human movement, so basically if you have a user, it connects to a base station, and then it goes to a radio server, which stands for Remote Authentication Dial-in User Service. So we had access to this server. So we were able to look at all data and all information about users. And then if the user moves from point A to point B, within the same session, we are capable of seeing this handoff, and we can basically understand the location of a user. And then we also had intersession movement. That means the user accesses a given base station. Then the user switches off, but then moves to another location. So we are still capable of getting this. And what we argue in the paper, that despite the fact that we had this sampled kind of behavior, that even if you have, if the users are not online all the time, that they switch on and off, we are still capable of capturing their basic mobility properties. I'm going to leave the arguments along these lines for one-on-ones if you're interested. So then we use rule mining techniques to basically go on and understand basic moving properties. So here we simply define a group of users who sit at point A, and then they access a given service within a time window W, and then they are seen in another location within within interval delta. So for these users, we basically we go on and define a rule movement like this. Then we have a stationary movement. I'm not going to talk about that. That just means users stay at the same location. And we have a disappear rule, which means users just switch off and they're no longer here. They're no longer in the picture. This is a better way to show that. So basically here we have position A. The rule support is the number of people present at A at a given point in time. Then these users move to location B. Now rule confidence is the number of people that move from A to B. And finally, rule support is the confidence probability is confidence over the support. So the larger the confidence probability, the larger confidence that this rule has some meaning in this particular case. So let me show you just a few, just some of the results that we had. I'm not going to dive into details, and I'm not going to tell you, give you the whole story. If you're interested, I can send you a paper. So basically, what we see here is there are two y-axes, y1 and y2. So y2 is the total confidence of rules. So here you can see that, for example, here you have 37,000 people. Basically, this is 31,000 people and so on. And then this particular graph is associated with this particular rule. So what we see is that on a Wednesday, you see these peaks happening at 8 a.m. and at 5 p.m. And basically, what is going on is that, of course, users are more likely to move in these particular times, while on a weekend, on Sunday, you can see that people are most likely to sleep longer, and they're less likely to move longer, because you can see here that that this is much smaller than what happens during the workday, which is kind of expected result. So then we tried looking at, like, okay, what is the correlation between applications that people access and their mobility properties? So what we have shown, one strong rule that we have found is that weather is a good indicator for stationarity. Like close to 70% of accesses remain at the same location for the next 6 hours. So once you access weather, you are most likely to stay at the same location in the next 6 hours. And then we were kind of trying to understand why this happens. And then we realized that one possible reason is because it's Chicago, right? So once you see what the weather is outside, you don't want to go anywhere. You just want to stay home for at least 6 hours, right? So we don't know if this result is of a more broad scope. So basically, we need another location, something like San Diego or something nicer, to understand if this has a strong local implication. So another finding is that maps are a good indicator of movement. 67% of users accessing the service can be seen moving in the next 3 hours. And then what we have found is that there is a strong correlation, anti-correlation between of given applications and basically mobility properties. So stationary users tend to access music downloads a lot, while mobile users tend to access email a lot. So we try to look into this in somewhat more detail, and here is the result. On x-axis, we have the number of base stations seen by users. So this is 1, and this is 50. This is over 1 week period. And then on y-axis, you have application access probability. So what you can see is that those who access music are mostly stationary users. As the mobility increases, they're less likely to engage into this kind of downloads. So now we were unable to understand why exactly this happens, but there could be 2 reasons. One, because people are unhappy with the bandwidth that they get when they are moving a lot. If this is the case, then these peer-to-peer kind of mobile applications might have a lot of success because they can improve throughput in these particular scenarios. But if the power or the battery is the concern, then this is not the case. Yes?
Is this probability within applications or across time? What does 50% mean on the y-axis?
Of those who see only a single base station in the 7-day period, the probability to the cumulative number of accesses to all applications. This is the percent of music downloads.
So this doesn't say whether that you tend to check more email when you move. It just says that the fraction of times you access email as a fraction.
No. This is the fraction of accesses to application.
The denominator is all accesses to applications, right?
Yes.
So the absolute quantity could still be the same? The absolute number of accesses could still be same? Or not? In the numerator?
So all these things sum up to 1.
I see.
At a given.
So this is all relative use. It says nothing about the absolute use of application.
Yes.
It may well be that even when I'm stationary or mobile, I check email exactly the same with exactly the same frequency.
Maybe, but
Yeah.
but this is relative to all the users at a given.
Sure.
Yeah. That's right.
But it's, yeah.
Yeah. So yeah. I mean, we're on the same page. So the second insight is that the more you move, the email becomes a more dominant application. And then basically what we have said is that, okay, if you are moving a lot, you see as much as 50 base stations during a week. That means that you are really moving a lot. That means that this particular device, mobile device, becomes your computer. So that's why you probably are checking mail more than others, right? So for stationary users, we believe that they may have some other stationary desktop or something else that they're using to access this. We found another interesting point for social networking, which kind of is in between the two. So it just becomes big here. We are not sure how significant this is, or we were unable to come up with anything more insightful than that. Okay, so we had other insights here. If you're interested, I can send you. I can send you a paper, or we can talk more. Okay, so the final piece of my presentation is about infrastructureless indoor positioning. This is a work in progress, so this is still not finished. This is a project that I'm working with my students. So to motivate this problem, basically we have seen that you can have good positioning when you are outside. GPS works, everything is fine. But once you go inside, it doesn't work so well, or it doesn't work at all. So my personal problem here is that I have a 4-year-old son, and then I often have to buy chocolate milk for him. And then I go to a grocery store, and they have chocolate milk at 2 different places. One is in the fridge, and the other is totally outside the fridge, right? Where you have these 12-pack kind of things. And then I go to the fridge. I always buy from there, and then my wife kills me at home telling, like, why didn't you buy these 12 packs? They have it somewhere else. I have no idea where they are. And once I spent like 20 minutes walking around that grocery store trying to find 12-pack chocolate milk, I found it finally. But at that point, I told to myself, okay, this is a problem that people are having. I'm a human. I have a problem. I want to solve the problem. So basically, the question is, how do you do indoor position? So we are not the first, of course, to look at this problem. You have a number of different approaches. Triangulation is one. Of course, if GPS doesn't work, then you have to have some other infrastructure. For example, you can use cell towers like CDMA approach. I believe you had a paper along these lines. And you can also have, or you can put some infrastructure inside the building, right? Where you can, once you have infrastructure inside, you can again do triangulation. You can try to understand what is going on. What your location is. Then you can have these RF signatures, for example, beacons. You can go, when you see a Wi-Fi network, you are in that range, you can say, aha, approximately this is where I'm now. So you can basically try to understand where you are. Or if you don't like infrastructure, you can go on and send a radio signal within the room. And then you pick up the response from that radio signal. This is kind of a fingerprint of a given location. And then you say, aha, this is where I am. So now you can do that. Now the problems with this approach is that you need infrastructure, which is not a small thing, and you need manual labor, right? Somebody has to go on and fingerprint the entire space, which is not easy. It's not easy because, for example, here, if you have 2 points that are very close to each other in space, the the response here in delay and frequency domain can be very different, right? So it's not easy to do this kind of thing. And if you go to a grocery store, in my favorite food mart where I want to buy chocolate milk, and if you tell them, how about you guys have some infrastructure here so that we can understand where the chocolate milk is, they will tell you that's fine, but if you want to implement something, if you want to give us money to deploy this, that's fine, but we are not going to do that on our own. We don't care about that. So basically, what we are trying to do is try to come up with a practical kind of solution to this problem. So the first thing is let the building owner off the hook. We don't want to talk to the building owner, right? We don't want to install any infrastructure. We don't want to ask for any detailed schematics, right? We don't want to do any fingerprinting, cancel the site surveys, don't build detailed RF maps. And then we just want to rely on what actually can work in reality, which is let the users report what they see, right? So in this particular case, you have two examples. One is the Whole Foods in Evanston, and this is Hyatt Regency O'Hare Hotel. So basically, many of the facilities publish free floor plans, right? So what we are saying is that if you can use precomputation, you can extract information from here, and you can use people to help you navigate to understand where they are, right? People are great noise filters. For example, if you're standing here, like if you send a radio signal and you have people around you, it's going to get distorted and everything else. However, if you have a human here, it will tell you, aha, I see seafood here. So this can be used to basically do indoor navigation. So here is an example. Here is my favorite grocery shop. There you see olives. There you see self-service serve counter. Based on this information, you already have some understanding of where you can be in that space. And then, again, there's another example, wine and olives. And the bottom line is that you can take advantage of the relationships among identifiable features in the room. What that means is that, I mean, we're not trying to land a spaceship on a moon on a particular point, or we don't want to kill somebody with the exact, we don't need a millimeter level kind of precision. What we need is something that can be useful so that people can be navigated and say, aha, go here and then go left and then go right, and then you find a given whatever you're looking for. So let me just give you a brief, I'm going to be done in less than 5 minutes. So basically what we are looking for here are some important definitions. So isovist is the visible area from a location, right, from a given location. So here we have 3 isovists, green, blue, and red. So basically here you have points. I'm not sure if you can see them. The green area is all the locations that you can see this point from, right? And you can have some features, such as landmarks, such as, for example, cash register, bathroom, elevator, whatever else. And then we define the region as a subset of coordinates sharing an identical feature vector. So here is what it looks like. So the bottom line is that if you see a given feature, then that feature sees you, right? So for example, if you have, for example, here 3 features in this particular room, it can be shown that there are 2 to the h minus 1 locatable regions for these features. And for example, assume a user says, I see A and B but not C, you're going to end up with this particular region, right? So you have already limited the potential location where a user can be for a fairly small number of features in the room. Now, if you increase the number of features, what happens is that it becomes even better. So for example, user can say, I see A and B, but not C and D, right? So you end up in these smaller regions. And the bottom line is that the more regions you have, the smaller the area at which the user can be. Now, the problem with this approach is that this assumes perfect reporting, right? So a user tells you, I see A and B, and I don't see C and D. Now, what can happen in reality is that the user can really see A and B. It might see C, but it's not reporting, right? I mean, you can have a number of features in the room, so you just don't report that. So the question is, if you don't have this perfect reporting, how the thing can work. So I'm going to show you quickly a brief example. You can see that. So here is my favorite room. So for example, assume a user says, I see specialty seafood, and then I see produce, right? So here, you don't assume perfect reporting. You just assume so that the user will tell you, I see exactly A, B, C, D, and I don't see this. You can't get that from the user. But even if you get this fairly not so fine-grained information, you can still end up with a region that is fairly smaller. Only with three particular features here, you can end up here. You see, you can be here, 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 or here and here and there. And then based on this information, you can go on and either ask more information from a user or use dead reckoning or other stuff to go on and reduce this space and so on. So I will give you just briefly. So basically, this is what the system looks like. You go on and basically download a map from a given company website. Now, again, this doesn't have to be a very nice map. This is just a coarse-grained map that can do the job. And then we pre-process this at our server. You download this, and then based on some user feedback, you can go on, and we can go on and help you understand where you are. Now, this is work in progress. And then what we are using, what we are trying to do is to add some additional user input or use dead reckoning to break the tie. Basically, we are building a very small sensor that we're going to put on a user in an attempt to try to understand how it is going.
I don't see how this helps you to locate your chocolate milk or so. I mean, if I have a map where it already says, here's the chocolate milk, and here are all the other important features of that store, then I can just locate myself. I mean, it's not difficult, and I can figure out the way for myself. So the kind of tool you showed that helps me to locate myself in a store based on what I see right now, it doesn't help me to find that chocolate.
Sure. But you see, once you find the chocolate milk, you can tag that map with that information and push it back to our website.
Yeah, I know. I understand that there's a process of what I see and how I can add information to that and how such a map is useful, but I don't see how the location tool is useful.
I'm sorry, what?
The tool that you showed us to locate a human being in that supermarket based on what the human can see at that point.
So once you know where you are, and you know where the given target is, then you can go on and guide the user, the client, and say go left, go right.
But I'm saying this is something the user can trivially do, him or herself, because if I get to see a map, I can locate myself. I don't need a computer to do that for me.
Where does a map come from?
By mapping the features. I'm saying I don't need a computer to do that. If I have a map, then I can locate myself in that map.
Not necessarily. I mean, you might be able to do it. That's nice. In a supermarket, yes, but you can have a huge mall. You can have a number of different places where it may not be as trivial to do that.
That's right.
Right? So, yeah. So, let me conclude the talk. So, I gave you 4 different stories. I hope you survived that. So, the first topic that I talk about is unconstrained endpoint profiling. The key point here is that try to harness information that is already available on the web. As Ratul said, it's not perfect. For some applications, it works better than for others, but it is definitely, it can be very helpful in trying to do traffic classification to get some external information, and a lot of that information is available on the web. Behavior-led targeting, again, it was a legal issue that we used to come up with a research problem. The bottom line here, and my argument is that we need more fairness in this, all these things in this area. Location-based services, we had a measurement study along these lines, and I think we have shown that there is a strong potential. We have found some other insights that are not emphasized in this particular talk. That is that there is a huge correlation between the types of applications that you're accessing and the location from which you're accessing these applications. So it's not uniform. There is a huge correlation among these things. And then for the indoor positioning, the bottom line is that, okay, we don't need, we need a practical system. That was really the constraint here. How can we get there, right? So we have built a system that I hope we can use in the near future to actually help people do this. I have other projects. I'm just going to mention some of them. Of course, a great collaboration with Microsoft on glitch-free internet audio-video conferencing. We have found out that if you want to talk to somebody in Microsoft, you better go and talk to that person, go to his office, right? That's the best way you get the best quality. Otherwise, using voice over IP is not the best idea. No, I'm joking. I also have some collaboration with NSF and Google on net neutrality and with Cisco, so I'm not going to talk about that. I'll be happy to talk more about that later. So thanks for being here and for listening to the whole presentation.
Thanks for Alex. For the
They're about to leave.
Alex is going to be here for the next 2 days.
I see.
Basically, till Friday afternoon. Interested? Feel free to meet him.
Sure. Where is he sitting?
2975.
Somewhere there.
Yeah. I'm gone tomorrow. I'll come find you today sometime.
Good.
Should deploy your email system.
Yeah.
Why what?
Email system, yeah.
The feature is Alex.
You need to.
Good seeing you, man.
Hey, how's it going?
Enjoy.
Thanks.
I would think
Thanks for coming.